Hi, I'm Marcella Billick. Welcome to my first lecture entitled Consensus in the Science of Climate Change, Reality and Perceptions. My expertise is in plasma physics and materials engineering. Although I am not a climate scientist, my knowledge of the basics of combustion chemistry and light matter interactions is enough for me to understand why our planet must be warming as a result of the burning of fossil fuels. What is remarkable for me about climate science is not the science itself, but rather how it is being discussed in the media and in the general public. When I hear conversations about climate science, I hear phrases like, "You're entitled to your beliefs, but I don't believe in climate change." Wow. I don't hear comments like that about any other discipline of science, even the super hard to get your head around areas like quantum physics and general relativity. In this lecture, I would like to explore this bizarre disconnect with you. In general, science is not controversial. In fact, it is so well trusted that scientifically tested is a popular sales pitch used to convince people that a product is trustworthy. Why is that? One reason is that science has a long history of delivering on its predictions in the form of new technologies. Users of all the amazing technologies ubiquitous in our societies, such as generators, motors, computers, lasers, smartphones, medical imaging, GPS, are testing the predictions of many fields of science, such as electromagnetism, optics, and quantum physics every day. So not believing in the underpinning science is simply not a credible option. The ubiquitous successful applications of science verify the science. Even in cases where the science itself is truly weird and unbelievable based on our everyday experiences, such as quantum physics, its applications are very real and tangible. In quantum physics, objects are both waves and particles at the same time, and the state of everything can only be described by a probability function until a measurement is made. How weird is that? But nevertheless, if it were not true, computers, lasers, smartphones, GPS, and advanced medical diagnostics such as MRI would not function. So no one questions the bizarre theories of quantum physics. Very few understand them, but we all accept that they are true. Since the same science that underpins our understanding of climate change contributes to so many of the technologies we enjoy in everyday life, not believing in human-driven climate change is pure hypocrisy. Let's think for a moment about why science should be so successful at predicting real-world outcomes. Why is it typically not controversial? And why is it so widely trusted? I think that unquestioning trust of science is underpinned by the way science is done and by how its outcomes are published. All scientific studies are carried out according to the scientific method, and to be incorporated in the body of scientific literature, the outcomes of these studies must pass a peer review process. Examining and understanding these two processes should help us understand why science is so inherently trustworthy and typically not controversial. The scientific method has been used in the development of science since at least the 17th century. It is evidence and inquiry based. It starts with careful observation, applying rigorous skepticism about what is observed to prevent cognitive assumptions from distorting how observations are interpreted. Hypotheses or theories to explain the observations are then formulated and tested in experiments. The observed outcomes of the experiments are compared to the predictions of the hypotheses being tested, and discrepancies point to flaws or limits of applicability of the hypotheses. Hypotheses that don't cut it are discarded or revised until they do stack up. The same hypotheses and observations are rigorously examined in this way by many independent experts all over the world before they are accepted as science. Before any particular study is admitted into the scientific literature to be counted as a part of the body of science, it must pass the peer review process. The group of scientists who conducted the study write up a manuscript which is then sent to a number of international experts in the relevant branch of science. In a process managed by the editors of the journal, these experts anonymously communicate their appraisals to the authors, who are then required to address each of the criticisms and suggestions of the expert reviewers. These expert reviewers check that all of the relevant details allowing the study to be replicated are included in the manuscript. They check that limitations of the techniques used are properly taken into account and that uncertainties of measurements are clearly assessed and described, and that their effects on the overall outcomes of the study are quantified. The reviewers also check for inconsistencies with the existing body of scientific literature and require that any inconsistencies are checked by examining elements of the experiment that may have been flawed. Inconsistencies that remain must be well documented, and potential explanations for these must be suggested so that they can be explored in follow-up studies. To get the manuscript published, the authors must address all of the expert reviewers' comments convincingly. Here is a flowchart showing the peer-reviewed process. An article, as drafted by the scientists who conducted the study, is submitted to the journal at step 1. It then goes through a process for plagiarism checking at step 2. This is usually conducted by software. Once it's cleared of plagiarism, an editor will engage with a number of experts in the field internationally who will provide reviews of the article containing their evaluations and criticisms that need to be addressed before publication. Based on these, the editor will determine whether to reject the article or give the authors an opportunity to revise it according to the criticisms. This cycle may happen a number of times with a number of revisions and re-reviews by the experts. At some point, either the article is rejected or it is accepted, having been cleared by all of the reviewers and the editor. Once accepted, it enters a galley proof stage where the production team formats it according to the format of the journal. The authors get one more opportunity at step 6 to review these galley proofs and check for any typos or errors that may have crept in. And then in the final stage at step 7, it's published in the next edition of the journal and enters the body of scientific literature. Let's now look at the peer-reviewed manuscripts on climate science. A simple search in the Web of Science database for the topics climate change or global warming or greenhouse effect found 284,670 articles published since 1965. There are clearly a lot of works on this topic that have passed through rigorous peer review. And as can be seen in this chart that plots the number of articles published on the topic each year, the rate of publication of research by climate scientists has been growing at an increasing rate since the first works in the 1960s and 70s. Another database, Scopus, gives a similar picture, with almost 500,000 peer-reviewed publications found in a search looking for the words climate change or global warming or greenhouse effect in the title, abstract, or keywords. These searches suggest a mature field of research that should have reached a good degree of consensus through the application of the scientific method and peer review processes alone. However, because of all of the discussion in public and political spheres about controversy in this field, a further field of study that seeks to examine and quantify the level of consensus in these publications was born. Wow. There is no other field of science that I know of where there are independent studies to try to establish whether or not there is a consensus in the science. The scientific method and peer review processes make such studies redundant, but because climate science is under attack, they are called for. Over the years, there have been a number of studies using scientific analysis methods to try to determine the level of consensus throughout this voluminous body of climate science literature. Here I describe the results of a few. A paper published in the prestigious journal Science by historian Naomi Oreskes found that there was a scientific consensus about the reality of climate change due to human causes. She ends by saying, "Climate scientists have repeatedly tried to make this clear. It is time for the rest of us to listen." Amazing that this was published in such a prestigious journal as far back as 2004, and we are still bickering about whether or not it is real. There have been many follow-up studies publishing similar findings. Doran and Zimmerman surveyed a large group of Earth scientists, finding that the debate on the authenticity of global warming and the role played by human activity is largely non-existent amongst experts in the field. Studies by Cook et al. In 2013 and 2016 came to the same conclusion based on abstracts of peer-reviewed articles and surveys of authors. They found that over 97% endorsed global warming caused by human activities. The percentage level of consensus increased with increasing expertise in the field of climate science. However, it was consistently in the range 90 to 100%. They noted that the level of scientific agreement on human-caused climate change is overwhelmingly high because the supporting evidence is overwhelmingly strong. The consensus is further endorsed by virtually all of the relevant scientific societies. Again, this is noteworthy because it is very unusual for scientific organizations to resort to making public statements about science. Again, it is because climate science is subject to so much unwarranted controversy in the public and political discourse that such statements by these organizations are viewed as necessary. I have included some websites that link to literature you can use to explore and verify for yourselves the scientific consensus on climate change. So in the final slide, I would like you to think about how public perceptions stack up to the scientific consensus. You could do a survey out on the street in your neighborhood or of your friends. You may already be able to make a guess based on comments you hear on the topic from those around you. Such surveys have been conducted, and public opinion as to the scientific consensus on human-induced climate change varies greatly depending on the community questioned. But in general, perceptions of the scientific consensus are way lower among non-scientists and way lower than public perceptions of consensus in other branches of science. I leave you with an article in the media which questions the accuracy of the 97% consensus estimation arrived at by the studies published in the peer-reviewed literature on the basis of procedural details. Articles in the press like this one that quibble about minor details are very effective at distracting audiences from the salient messages. In this case, that there is a strong consensus of the science of climate change caused by human actions, no matter how you seek to quantify it. By introducing controversy about largely irrelevant details, such articles very effectively portray a controversy where there is no meaningful controversy. Can you spot any other articles out there that create the illusion of controversy by focusing attention on details of minor consequence? In our next lecture, entitled Technology and Solutions, we will talk about what can be done to solve the problem of climate change. We will explore the remaining carbon budget and how fast we need to act. We will examine the state of the technology we have in hand to eliminate greenhouse gas emissions. And we will discuss the excellent roadmaps available for policymakers to take us to zero emissions over the course of a couple of decades. Thanks for watching, and I look forward to seeing you again for my second lecture.